Today we're going to start talking about acid-base properties of salts. Usually you probably don't think of a salt as having acid-base properties, but in fact, because they are ionic compounds, they do dissociate in water. And because they dissociate in water, depending on the ions they form, they may exhibit acid-base properties, which remember, hydrogen ions would make it acidic, hydroxide ions would make it basic. So if those salts have those kinds of ions within their structure, then they could potentially have some acid-base characteristics. So when we encounter a salt and we're talking about equilibrium, we have to ask, is it going to act as an acid or base, or is it going to remain neutral when it dissociates? So the example I have for you here today is sodium nitrite. It breaks up into sodium ions and nitrate ions, sorry. Remember that they have conjugate acid-base relationships. Strong acids and bases, we have said in the past, have weak conjugates. All the alkali and alkaline earth metals, however, are going to exhibit no acid-base properties. That's an important sort of statement that you need to remember. When you encounter an alkali metal, remember that's group 1 atoms. If you encounter alkaline earth metals, those are group 2 atoms, then they're going to exhibit no acid-base properties. And this would be in terms of salts here. The nitrite ion, remember, is the conjugate base of a moderately weak acid. Remember, these Ka values are relative, so they're comparing one acid to another. So a nitrate ion would be very strong acid. That makes nitrite with its Ka value 4.6 times 10 to the negative 4th a relatively weak acid. So because of that, the NO2 will act as a very weak base. Your textbook has given you this relationship, the Kw is equal to Ka times Kb. And remember that you have tables 14.2, 3, and 4 in your textbook that give you all kinds of weak acid and weak base information that you'll need in order to calculate the Kas and Kbs here. So when you go through these, look at all those typos I have there. when you have to calculate the Ka or Kb for the ion of a salt, you have to use the given values of a conjugate neutral acid or base. So we'll practice all these, of course. First of all, let's practice calculating Ka and Kb as required. We're also going to write out the reactions for the ions that we see here. And I got tired of typing superscripts and subscripts, so I'm just going to write them here. So the first one we're going to work on is NO2 negative, the one that we just looked at. If you think about the acid that is produced, it would be, or producing this anion, it would be HNO2. And the Ka value for that is 4.0 times 10 to the negative 4th. So if this is the information that we are given, then let's calculate the Kb and write a reaction. So first of all, if I take NO2, we'll start with the reaction, aqueous, and we add water to it. We are going to get HNO2, aqueous, and OH negative. So then from the Ka value, remembering the relationship that we just looked at, Kw equals Kb times Ka. We know the Kw is 1 times 10 to the negative 14th. So knowing those two pieces of information, we can calculate the Kb. So if you would like, you can rearrange the equation. Kw over Ka equals Kb. So 1 times 10 to the negative 14th over 4.0 times 10 to the negative 4th. So that's the Kb value. If you're just joining us, just in the chat box, just say, yes, I can hear you. We were having difficulty, so that's just my question today. Can you hear me now? Okay, so calculating that, we get 2.5 times 10 to the negative 11. So this exercise is having us first write out the equation for the reaction with water, and then finding the Kb given the Ka, or vice versa, depending on the ion. Okay, so let's take a look at the next one. Why don't you try B on your own? I'm going to pause for a second. You set it up, calculate, write your equation, and do it for your own practice. When you get an answer, you can put it in the chat. I guess I have to give you stuff, don't I? Ka equals 7.2 times 10 to the negative 4th. And this is for HF, the acid. Okay, now you can go forward. Courtney, what is the reaction that you would write here, and what is the final Kb that you were able to calculate?
Okay, so it's F minus aqueous plus H2O. And then on the other side, HF plus OH minus. And then the final Kb 1.4 times 10 to the negative 11th.
Very good, thank you. Okay, so those are both acid examples, finding the corresponding Kb value. Now let's take a look at a base. So here is a base for you. This is aniline, C6H5NH3+. And the Kb is 3.8 times 10 to the negative 10th. And that would be 4 C6H5NH2. We're taking this ion, we're adding it to water. And the resulting the water here is taking on the hydrogen. So then using our equation, this time it's Kw over Kb equals Ka. So it's 1 times 10 to the negative 14th divided by 3.8 times 10 to the negative 10th. And that is the Ka, which when you calculate it, it comes out 2.6 times 10 to the negative fifth. Over here, you know, you can also just write this as H plus aqueous. You don't have to write it as H3O plus. Okay, so pretty straightforward. Let me have you try one on your own again. This one is imidazole, HC3H4N2 plus. The Kb value is equal to 1.11 times 10 to the negative seventh, and that is for imidazole C3H4N2. So I will pick on Faith. So when you get this calculated, Faith, unmute yourself and walk us through the equation and give us the final Ka that you would get here.
Okay, so I don't know if this is right, but this is what I got.
Okay.
So you have HC3H4N2 plus H2O yields C3H4N2 plus OH. And then the Ka would equal what?
It is not OH in this particular thing. Notice the hydrogen here is going to be stripped off by the water, and it's going to make H3O plus.
Okay. So then I got 9.0 times 10 to the negative 8.
That is correct. I'm sorry. My book actually has it messed up. So you're right. 9.0 times 10 to the negative 8. Oh, but that's not B. Sorry. It should be Ka. And there we go. All right. So that's pretty straightforward manipulation. Sometimes those equations can get kind of tricky. I guess the clue here is you have the Kb, so you're looking for a Ka. So your reaction should reflect a Ka. So you wouldn't have OH in the products, you would have H. So somehow you have to figure out how to do that. So keep that in mind as you're working through those. The bottom line on these is you have to decide how each part, the cation, the anion of the salt, will react with water. Sometimes you actually have where both the cation and anion exhibit acid-base behavior. Oh, there's another lovely typo. Such as ammonium acetate, which ammonium acetate is NH4 C2H3O2. So NH4OH would be a base. HC2H3O2 is acetic acid. So in this case, it's a little tricky situation. And your book talks about this one where it exhibits both acid-base. And so when you calculate the overall pH of this solution, you have to use both values because they're going to affect the overall pH. Okay, so our next task then is to predict acid-base behavior, and then finally we will calculate the pH. So in this exercise, you'll need to look at data from your textbook. This would be the tables 14.2, 14.3, 14.4. That's where you find all the weak acid base data. So in the first one, we have sodium phosphate. So that would be Na3PO4. With water, it would break into Na and PO4. So we have to ask ourselves, okay, in this salt, what does the sodium ion do? Well, we know that alkali metals, we just learned, exhibit no acidic or basic behavior. The PO4 -3 comes from H3PO4, which if we look up the Ka value in our text, we remember this is one of those polyprotic acids. So I'm shuffling paper to point you in the right direction here. Phosphoric acid, remember, it's on page 689, has 3 Ka values. But this is a weak acid. So even without looking at just generally knowing it's a weak acid, the conjugate base would be fairly strong. So here we have a fairly strong basic solution. The next one, potassium iodide, is Ki. K is an alkali metal. So again, no acid-base characteristics. The I negative also exhibits no acid-base character. So this solution would be neutral. All right, let's look at the next one, pyridinium chloride, which has the formula HC5H5NCl. So looking at this, we have chloride ion. We also have HC5H5N. The pyridinium ion. It's the conjugate base of pyridine, which is C5H5N. So Ka equals Kw over Kb. So we could look up these values. And when we did, we would find out that the solution is acidic. And again, I would point you to your tables. Your tables would have the Kas and Kbs of these weak acids and bases, and then you can kind of figure out what to do with them. The last one here, ammonium fluoride. So if we look at ammonium fluoride, NH4F would make NH4. Here, let me put the water in. Plus water gives you F minus plus NH4. I'm not sure that the water helps, so let's take it back out. Okay, so just looking at how the ions dissociate. So we need information about F and we need information about NH4. So remember, NH4 is a conjugate acid of NH3. So we can look at that. NH3 plus water gives us NH4 plus OH. So the conjugate of NH3, if we figure out the Ka using the Kw over Kb, we find out that Ka for this reaction is 5.6 times 10 to the negative 10. In terms of the F, it's the conjugate base of HF. So if we look at that, HF breaks into H and F. So it's a conjugate base of HF. HF, if we use the Ka value to calculate the Kb, so in this case, it would be this. We find out that the Kb is 1.4 times 10 to the negative 11. And we're just using the processes that we just practiced in the previous. So here, Ka is greater than Kb. So Ka would be, since it's this right here, it's a weak acid. So here you're kind of putting quite a few things together, dissociation equations, plus you're looking at how to relate Kb and Ka, and then determining what the solution's character will be. So a lot of kind of pondering the situation here in a little more detail than you probably have practiced. Okay. So the last kind of problem that we need to work through is how to calculate the pH of a salt. So this one is sodium nitrite. The Ka value is equal to 4 times 10 to the negative 4th. And with that information, we can proceed similarly to what we've done before. So this is sodium nitrate. Earlier, let's go back. here's the NO2 ion of the sodium nitrate, because remember, sodium is an alkali metal, so it's not going to affect the pH. It's only going to be the NO2 here. So the NO2 reaction that we wrote here in the beginning is the reaction that we want to begin with. So I'll rewrite it here on this page. Sodium not affecting pH. It's a really bad sodium. So it's the NO2. So we put it with water. It produces HNO2 plus OH. The KB, this is a basic reaction, is products, HNO2, over reactants. Remember, you don't have to put the water. We can use the Ka value here to figure out the Kb using that little relationship that we've been practicing. So it's 1.0 times 10 to the negative 14th over 4 times 10 to the negative 4th. That's going to give me the Kb value. This ends up being 2.5 times 10 to the negative 11th. Now we can proceed, now that we know the Kb, we can proceed as we normally would with our equilibrium problems. So I'm going to take this out just so I can make an ice chart underneath. So initially we have 0.5 molar NO2. We're not going to worry about water. We have 0 of these. The change minus x plus x plus x, 0.5 minus x, x, and x. So now we can plug that into our Kb. So 2.5 times 10 to the negative 11th equals x squared over 0.5 minus x. We can solve using our assumption that the x here at the bottom is very small. So 2.5 times 10 to the negative 11th x squared. So x, which is equal to the OH, but also the concentration of the HNO2, comes out to 3.5 times 10 to the negative 6. So it's going to pass the percentage rule because Kb is so tiny. So it's going to be within the 5% rule. So then to get to pH, we will have to use POH, the negative log of the hydroxide concentration that we just found here, 3.5 times 10 to the negative 6. And that will be 5.45. Then we calculate pH from that, remembering it's 14 minus the 5.45. and we get 8.55.